This video is about parametric equations, and we are looking inside of our trifold, and we're looking at the second panel, the middle panel, when we're talking about ellipses. So we can see that we have an equation for an ellipse. We also know by our information about ellipse, because A is underneath the y's, this is going to be a vertical ellipse, so it's going to look something like this. So now that we know that, let's see if we can rewrite this. And I'm going to rewrite this as x plus 3 over 4, and then the whole thing squared. That will give me my x plus 3 squared over 16. And I'm also going to rewrite the second term as y minus 1 over 6. Again, the whole quantity squared is equal to 1. So using our trig identity that sine squared of t plus cosine squared of t is equal to 1, I'm going to use substitution by letting sine of t equal to x plus 3 over 4, and then solving for x. So when I do that, I'm going to get 4 sine of t is equal to x plus 3, or x is equal to a negative 3 plus 4 sine of t. So we're going to do the same thing for our y's. So we are going to let cosine of t equal to y minus 1 over 6 and solve for y. So I get 6 cosine of t is equal to y minus 1, or that y is equal to 1 plus 6 cosine t. So now I have my equations, an x sub t and a y sub t. These are my parametric equations. So I'm going to go ahead and put these in a calculator so we can see what we get when we graph. So remember, we need to make sure our calculator is in parametric mode as well as that we are in radian mode. So when I go to y is equal to, we are ready to input our x equation as well as our y equation. So for our x of t, we're going to have negative 3 plus 4 sine of t. And for our y equation, we're going to have 1 plus 6 cosine of t. Doing a zoom 5 and doing a zoom 6, we can see that our equation of our ellipses here, again, we should notice that it is a vertical ellipse, slightly. So now we can see our equation. One thing we can notice is that we used this relationship of sine squared plus cosine squared is equal to 1. We could have easily have used that it could have been cosine squared of t plus sine squared of t is equal to 1, meaning that when we were solving for x, we would have gotten x of t is equal to negative 3 plus 4 cosine of t. And then the y value, we would have had 1 plus 6 sine of t. Now I claim that we will graph the exact same thing, so I'm going to go ahead and put this onto my graph as well as a second set so we can see that it's going to graph the exact same ellipse. So for our second set of parametric equations, I said I'm going to do negative 3 plus 4 cosine of t and a 1 plus 6 sine of t, and have them graph both of these equations. So the blue one's already done, and notice the red one is right on top of it. So I want to show you each of these individually just so that we can notice what happens when we change that sine and cosine. So first thing we're going to do is turn off the second set of equations so we can focus on the first set of equations. And I'm going to change the first set of equations so that it's still going to graph it, but I want to graph it and I want to see what happens to it. So I am going to change the line into what I call a snail with a trail. So the snail with the trail will actually graph it and then show you the direction in which it's graphing. So we can see that it actually went clockwise. If I go and do the exact same thing for the red one, so I'm going to come and turn it on for my second set of equations, and I'm also going to change the line so that it will be a snail with the trail. And then hit graph for that. Here we can see that it is graphed counterclockwise starting at the x-axis, whereas the blue graph was graphed going clockwise starting at the top of its graph. So we can see that. I also want to show you what happens when I change my window and I change it from 0 to 2 pi to 0 to 4 pi. I'm going to keep the same increments and we're going to see what happens when we graph. So it went around once and it went around twice. And same thing's happening to the red one, going around twice. So from here you can try it on your own with this new equation down here. Moving on to the third inside panel, let's say we have a hyperbola, we have an equation there. We know from our studies about hyperbolas that it is going to go up and down because it's going to be like the y-axis away from the x-axis. So we're going to expect a hyperbola that looks like this. Similar to the way that we did our ellipse, we're going to rewrite this as y plus 1 over 2 squared minus x minus 2 over 1 quantity squared is equal to 1. So unlike what we had before, where we had sine squared of t plus cosine squared of t is equal to 1, we need something that will subtract to 1. So in our case, we're going to use the secant squared equation. What does that mean to you and me? We're going to rewrite this by dividing everybody by cosine squared of t, cosine squared of t, and cosine squared of t. That will give me tangent squared of t plus 1 is equal to secant squared of t. So we want it to equal to 1, so I'm going to subtract the tangent squared. So I'm going to find secant squared of t minus tangent squared of t is equal to 1. So we're going to use this trig identity over here, meaning that I'm going to rewrite this as secant squared of t minus tangent squared of t is equal to 1. So by substitution, we're going to see that secant of t is equal to y plus 1 over 2, and then we're going to solve for y. So I'm going to get 2 secant of t is equal to y plus 1, subtract 1 from both sides, y is equal to negative 1 plus 2 secant of t. We're going to do the same thing over here. We're going to let tangent of t equal to x minus 2 over 1 and solve for x. And we're going to see that x is going to equal to 2 plus tangent of t. So we're going to stick these into our calculator. Big thing that we need to remember is that the x1 is going to have the tangent and the y is going to have the secant. So let's do that. So one thing I do want to mention that when I do put in my equations, I don't have a secant button, but I do have to use the 1 over cosine. So this is my secant right here. So before I hit graph, let's go to my window and make sure that I have it going from 0 to 2 pi. So this way we can see it just doing it one time. And then I'm going to hit graph. So we can indeed see that it opens up and down. Well, when we did ellipses, we switched around the cosine and sine and saw that there was no difference. So let's see what happens if we do the same thing here. So I'm going to have my x be a -2 secant, so it's going to be 1 divided by cosine of t. There should be a plus between the -2 and my parentheses of 1 over cosine of t. And then my y value is going to be 1 plus 2 tangent of t. So I left the blue one on so we can see if we're going to graph the exact same thing. Even though we graphed the wrong equation, we can still see that it was going to be a horizontal hyperbola instead of a vertical hyperbola. So one thing that we need to remember is that whoever has secant squared, or whoever has secant, needs to be first. So if you want it to go up and down, then the y value must be secant. If you want it to go left and right, then the x value needs to be secant. So whoever has secant determines which way our hyperbola opens. And with that, you can now try this last equation on your own. And that concludes this video.